compression. The compressor is then compressing that air, which in turn is then ignited by 3 injectors which throw in natural gas, and then the combusted air expands to the turbine. The turbine in turn rotates the shaft and producing 30 kilowatt of energy.
So what we did for my project, or our group's project, we did wave power in Superior. We did try to figure out what type of buoy would be useful in order to harvest electrical energy from wave motion, and we did a buoy similar to this, a magnetic shaft in an electric coil, working on properties of a solenoid to get electrical power. And we did that in the Marquette area based upon different factors such as average wave height, accessibility, shipping lanes, water depth, power demand, and of course the ever-dreaded ice formation. And from that we figured out that each buoy could produce about 8 kilowatts of power. But because of the high cost of manufacturing the buoys and how long it would take, it's currently not really feasible at this time.
Well, what we looked at was recovering energy from municipal water distribution systems. Currently, the pressure is regulated. You know, the pressure is not the same at the top of a hill as it is through the bottom of the hill. So you got to control that. Currently, they use throttling mechanisms to regulate the pressure, which dissipates a lot of energy, wastes a lot of energy. However, we examined looking at using hydroelectric turbines to regulate that pressure and extract energy, using the pressure head to turn the turbine and ultimately dump electricity back into the local community's distribution system. Limiting factor, primarily a function of the size of the area in terms of population, the flow rates through the system, as well as elevation change, you know, the pressure head in the system. The high capital costs generated a fairly long payback period, which is, a lot of case studies we examined were deemed not feasible because of the long payback periods. But with government grants, investment from outside sources, you know, you can shorten up the payback period.
For our project, we looked at analyzing 2 different processes for coal to liquid fuels and converting those. Through these processes, we convert coal to aviation fuel for a JP8 fuel is the standard. This is highly in demand fuel through the military. So our project was based around if the U.S. needed it, could we use a coal to liquid fuel base to help our military meet energy needs in time of an embargo, in times of a war, and things like that. Just one more step towards energy independence. So we did look at 2 processes. First, an H-coal process, which is a direct liquefaction, where you're going coal to fuel right away, and then a Fischer-Tropsch process, which you go from coal to gas to liquid. Overall analysis we found Fischer-Tropsch had much higher efficiency for the 2 processes, a matter of 12 to 78 approximately. Looking at the costs of how to do it based on how much energy you're going to need to fuel it. Again, Fischer-Tropsch had a much lower cost per mole of fuel and things like that. And finally, we looked at environmental impacts, where we looked at how much CO2 would be released in the processes. H-coal did have about a quarter of the CO2 released during the process, but due to these 2 dramatic factors and the fact that the CO2 could either be reused in the system or filtered out a little bit more, we decided Fischer-Tropsch would give the best option for a process to make an aviation fuel.
We did a project on determining the feasibility of a wind turbine farm in the Keweenaw Peninsula. As you can see, in the United States, some of the best wind is in the Great Lakes. And looking at just the Keweenaw, there's a pocket of very good wind that's close to the shore, about a mile out, and with a depth that's less than 60 feet deep. So we decided that we would locate a wind turbine farm there, and with all of the economic analysis, after upgrading the transmission lines, we got about a profit of about $3.5 million after 20 years with an initial investment of $13 million for a wind farm. That's 7 turbines, 7 850 kilowatt turbines that would be set up.
Using the flywheel as a means to store the energy for a turbocharger. And what this would do is this would keep the turbocharger running at operating speeds for longer, mainly during the time that you stop at a stoplight when it's going to spool down. This would keep it spooled up. So what you have, the thing we looked at was modeled a turbocharger and determined the amount of energy at the compressor that was needed to maintain those pressures in the intake. And then we also used the speed of the compressor and turbocharger to determine the amount of energy that the flywheel can maintain. So what we got from this is we got the work of the compressor, the energy of the turbocharger. From that, you can actually get the time need that it would maintain for. We tested 3 materials: carbon fiber, reinforced composite, titanium aluminide, and titanium. We picked an arbitrary size, 6 inches by 4 inch diameter flywheel, and what we found out is that they can only maintain this energy for like 13 seconds at the max, and that was with titanium. So I mean, it really isn't worth it because you want this to maintain for minutes. So when you're at a stoplight, you have this increased manifold pressure, which allows the engine to have a higher volumetric efficiency. We also found that the strengths needed in these materials is astronomical. We're talking about 40 to 60,000 RPM at the flywheel. So at those speeds, actually the titanium, it would fail, which means the stress on the surface of the titanium would rip it apart. The other 2 materials were fine, but you can still see that the amount of energy that it stores, for the amount of time is not really worth it. Also, cost of materials are really expensive. You're talking about titanium, that's going to cost $150 for the size we need, and also just all the modifications needed to the system would add to the cost. So it's really not flywheels aren't feasible for this application, but for more larger scale applications like regenerative braking in a vehicle, that could become a good application. Where you use the speed of the vehicle to spin up the flywheel, and then use that when you want to start moving the car again. So.